Good afternoon. I'm Andrew Smith. I'm going to be presenting on the discovery of latent 3D key points via end-to-end geometric reasoning. This was a paper done by a group in Google AI, and it was just presented over in MIPS 2018 not too long ago. So let's get started with a quick overview of what we'll be talking about today. Yeah. So we'll talk about the problem about finding key points. We'll go into the solution overview that they talk about in the paper, some of the details about the solution, a further dive into the neural net side of it, and then the testing methodology along with their evaluation of results. So to begin, just in general, in terms of 3D objects and finding key points and everything, it's usually been a supervised task wherein you're given a list of the 3D key points and your goal is to, approximate to those. And then another problem is that if you start changing the rotation or the transformation of the object in question, like for example you see these chairs, none of them are in the same position. The idea with that is that if you change your rotation, you want your key points to follow suit. So our goal with this is, can we learn the key points of a 3D object given the 2D image of the object, and can we also present them regardless of how the object is rotated or transformed or otherwise? So in order to accomplish this, we are to find an optimal set of 3D key points. As I said, without the ground truth, we'll be using some other sort of self-supervised method for that. And we'll begin to formulate losses for each key point detection. The two that we'll be taking a look at in particular, along with some others, are the multi-view consistency loss, so that each key point would be the same in different views, and the relative pose estimation loss, which I'll get into in a minute. So the overall goal with this eventually is that you want to be able to take in an image, pass it through the network, and then be able to get the list of key points. So just to recapitulate what I've just been saying. But of course, in this case we have an image I, which is of a 3D object, in this case a car. We know it's a car, so it'll be applied to the Keypoint Net that's based on cars, and it'll find the appropriate key points. The N is of course the number of key points. But of course, to train a network like this, we need a few more examples and a little bit more robust of a style. So to begin, we'll take another image of the 3D object. We'll perform a transformation on it, which can either be the rotation or the translation. We'll specifically be looking at the rotation during the context of today's presentation, and that's what they primarily use to get image I prime, which of course you can see is a different rotation of this car. Each image is passed into the Keypoint Net simultaneously, and we get a list of key points that we will begin to evaluate for our first loss. So for our first loss, we will be taking the key points themselves, performing a projection operation to project the key points from this image onto this image, and the key points from this image onto this image, and keep going with that, and then get a better list of key points. Once we have these lists of key points, we will combine them and perform some different matrix operations using SVD and a couple of other things to get an estimated rotation, which of course will be compared against with our ground truth over here. So a lot of stuff to cover. We won't go into the neural nets just too quickly, so let's start where we are given the key points, and now we want to make sure that the key points correspond to each other in the multi-view consistency loss. So as a reminder, the transformation matrix, is comprised of the rotation matrix, which is the 3x3 matrix. We have a translation vector, and of course a couple of other values to make a 4x4 matrix. This will be applied when we want to take different views. So here we effectively have the perspective transformation, wherein we give real-world coordinates in 3D to this thing, and then here we have the focal length of the camera that was used to take the image, which is a global. We divide by the depth, and then we end up with pixel coordinates over here. So in theory, if we take the inverse of this function, we should be able to get the 3D results. So that's exactly what we do to begin to do our process. So first we'll get the 3D results by putting the coordinates from the first image into this pi inverse. We will apply the transformation on that so that when we put it back into this other pi, which gets it back into pixels, then we should in theory get the projected coordinates onto the other image. And it follows that we can do the same thing for the other image with the u prime, the v prime. We just stick it in the inverse pi. We do the inverse transformation because we already used the other transformation up here. And pi, of course, to get it back from the real world coordinates, the 3D coordinates into the pixel coordinates. And then all that to effectively say that we want to minimize the distance between these projected coordinates and the real world coordinates. So real world coordinates over here, and then the projected coordinates over here. Minimize the loss, and we're pretty much golden. So that's a lot of math on one page. So to basically put it into different perspective, if we have our cars from before, and we decide to have the key points right here, so let's say that this is this key point right here, and then this one is this key point right here, and then we apply these pixel projections, then we should end up with something like this, wherein this one got mapped to over here, and then this one got mapped to over here. And we of course want to minimize the distance between those two to get some optimal projection results. And so that if the projections are equal to the originals, then the key points are good, and that's what we want. So moving on to pose estimation. After we've got all of our good key points, then we'll be taking those in. These are the key points from the first image, and these are the key points from the second image, and as you can see, key point from the first key points, I can key point all the way on through, and then a similar thing for the x prime for the other image. And so what we'll do is we will multiply those two matrices together with the transform, and we will then take the singular value decomposition on them, such that we end up with these two values here, because it will decompose the matrix such that we get two orthogonal matrices along with the diagonal. We want the orthogonal ones here. And we will use those to compute another matrix, which, as I mentioned before, we want to get the relative transformation of the entire set of key points. So that's exactly what we're going to be calculating right here. So we have this v from that came here. We take the diagonal here with all ones, and then the determinant from VU on this side, and then U again over here. And that will give us our estimated rotation. So it follows then that we'll be comparing it with the ground truth rotation right here. We will apply a Frobenius transform, the Frobenius normal, and we'll put it in through here, and we have this arcsine function which will effectively get the value into an angle measurement, such that that will be the angle that's in between where the ground truth matrix lies and where the calculated rotation lies. And we of course want to minimize that loss so that it's close to the original as possible. So in doing so, we did the key point calculations from before. We should be able to calculate the key points just that way anyway, so that's pretty good. But let's talk a little bit more about the key points. So it's pretty obvious that not all key points are going to be in the exact same place on every single image of every class or in every object. So we're going to have some sort of heat map function. And the way we do that is that we have these Gaussian-like functions here that are applied to each coordinate of every pixel of our key points. And we want to optimize where they're key points. It's very similar to in our first paper where we had some metric right here. The only difference here is that for us our range is going to be from 0 to 1 instead of -1 to 1. So that's that. And then we do a pretty similar thing for the depth where it's some sort of, what is it called? Probability distribution, Gaussian-like function to get whatever would be close. All right. Now, something else about our key points is that we want them to be distinct. So that means if we have two key points that are very close to each other, we don't necessarily want them to point to the exact same spot in the image. So we want to maximize the space between key points, and to do that, we'll take the difference of these two and then compare them against this threshold here. If they're too close beyond that threshold delta, then those key points are too close. We're not going to want those. So that's what this separation loss is calculating. Another thing is that we want to make sure our key points are actually on the object we are trying to find. So that's what this next loss function is for. This B function right here is a binary, which will take in the pixel values, and it will determine if the value at a given pixel is showing a foreground object or if it's just a background. So that's what that is used for. And then this is just a general variance function to make sure that we're getting good values that aren't necessarily from just a plateau of everything. All right, so now let's talk a little bit about the neural network that was at the beginning of or at the leftmost side of it. So this will apply, of course, to the training and testing, but for ease of explanation, I'll just explain with the one image. So take in a 128 by 128 image, perform some dilated convolutions on them. Each of them have a kernel size of 3, and you apply a leaky ReLU and a batch normalization on them, and you get 64 channel outputs. And then your last one, your 13th, will have 2n, which will correspond to the pixel coordinate key points. So remember how I said we get a 3D-like representation from the network? So this is where our Gaussian function I mentioned and the depth function come in, because those will begin to calculate the overall heat map, and thereby the pixels, and we'll also get the depth from the pixels into our last, of course, 3D. So yeah, this is just a recap again, just to make sure we've got all the pieces together. Image with the transformation into the Keypoint Net that's got those functions, including the Gaussian and the depth function. The consistency loss where we project across, and then this where we do SVD and calculate the rotation and then compare against the ground truth. So now that we've gone through all that, let's talk a little bit about the way that the authors in the paper had tested this. So the ShapeNet dataset has about 51,000 3D models from 270 different categories, different classes. So what they did is they took about 200 images, not about exactly, they took 200 images to create 100 image pairs, each with a different camera rotation around the object so that you get different views of the object. And basically what they did for their evaluation scheme is they compared against a supervised method. So in order to do this, they sent 3 of their classes, which I believe were the car, the chair, and the plane classes, to Amazon Mechanical Turk. They had 3 different people select key points. They took the average of those, and those are the ground truth that they'll be comparing against. And something else they also have to do to take into account is sometimes with the supervised method you need to specify an orientation such that, if you're looking at the left side of a chair or the left side of a car, you might not be able to differentiate it from the right side or even like the front or the back. And so the metrics that they use for their evaluation scheme is angular distance error, which is calculated very similarly to the rotation loss, and the 3D standard error, which is more or less a Euclidean distance between the key points that are calculated and that are the ground truth. All right, so now for quantitative results, the part that I'm sure everyone's most interested in. Lower is better on these metrics. These are, of course, mean and median angular distance errors, so these all represent an angle for these two, and then this is just the distance from the key points overall. And so as we can see, we just get better and better. And it's interesting because even when the orientation metric that I mentioned, we applied it to our method to the self-supervised method, and it didn't seem to make a difference. It actually did better without that, at least in one of these cases. So planes pretty much tell a similar story, and chairs, very simple. Very big gap between the supervised method and the unsupervised. So let's see that in a histogram format. So these are, again, the angular distance errors. We want them to be as left skewed as possible. And you know, the supervised method is pretty good, but it still has about, let's say, 30% of its values past 15 degrees of rotation. It gets slightly better with the orientation part of the network, or the orientation flag. But once we get into the unsupervised method, we can see that it's just growing. Like this one is above 0.4% over here, and even here, over half of it was very good. So pretty good results, I would say. Now let's show some qualitative results on different models. So in terms of planes, we see that like the left wing tip is consistent all across the views. And this right engine, for example, will show up here, and even though it's not perfectly visible, will still show up here as well. For chairs, as I mentioned before, we want to see that all the key points show up. So like this right leg will show up even though the view is occluded, which is pretty good. And the same story for cars. And this is just to show that no matter what view the object is in, the key points will still typically show up in normal objects. The thing about it is that, as I explained, it's just using this raw images during testing. It's not paying any mind to optical flow or like time data or anything else like that. So all those are being computed just from the straight images. Now let's talk about a couple variola cases. As I mentioned, the orientation thing is a big issue. So like for the first case, can any of us really tell what's the front of the car, what's the rear of the car? This network confuses that a little bit. As you can see, this is nowhere near this is. Actually, wait, that's not a... So something like this, actually. These purple points right here. And then on this plane, spaceship sort of thing, the first thing I noticed immediately was that these light blue key points aren't even in the same positions. So it's just very strange because you have these weird shapes and they're not exactly able to be tracked as easy. All right, so a couple different results that showcase how adjusting the losses affect it. So this is just the way it is normally. This is if you double the noise for the pose estimation loss. As you can see, the key points get spread out from the center a little bit more. If you reduce it, they'll cluster in towards the center, and if you just remove it altogether, it'll completely cluster. And then for the other thing I mentioned earlier, that we wanted to keep all the points on the object, well, say we get rid of that constraint. They'll go out off of the object, but the interesting thing is if you do any rotations or anything else on this, they'll still show up in the respective views as you rotate it, which is pretty cool. Some additional results, so like warping the actual 3D models. I think those are kind of interesting, self-explanatory, that they stay able to get the approximate key points even if the object itself is not normal. And then this just shows a comparison of how adding key points to the models explains. So if it could be as simple as just getting the nose, the left and right wings of the aircraft, but as you get even higher, it'll start tracking like the engine positions or even like the cockpit or the side doors on the aircraft, which I think is pretty interesting. And then this just shows some of their preliminary results as a proof of concept to show that this could even be applied to the real world. So for these sets of cars, the key points are pretty accurate and show up where they need to show up. But if you'll notice, like depending on the angle that it's being shot at, or even if like there's too much reflection coming from the car, specular highlights, that sort of thing, then the key points down here aren't necessarily calculated as accurately. So, of course, go to their GitHub if you want more information on that. So, to conclude, we talked about a semi-supervised end-to-end key point finder because, as I said, you know, the supervised methods, they would have stuff that was completely separated. You know, they would have a separate key point detector, a separate geometric reasoning architecture. This just combines everything and it makes it really easy. And for all that, it outperforms the supervised method, which is really good. So that concludes my presentation. Thank you.